Hello and welcome to this video on ImageNet-D. In this video, we'll delve into this new dataset. ImageNet-D is a benchmark dataset designed to test the robustness of neural networks using synthetic images. Unlike earlier datasets like ImageNet-C or stylized ImageNet, which focus on specific corruptions or textures, ImageNet-D takes it further by generating images with diverse backgrounds, materials, and textures using diffusion models. Here's what we'll cover today. A brief introduction to ImageNet and the challenges that led to the creation of ImageNet-D. The dataset generation process, including an explanation of diffusion models and the workflow used to generate the dataset. A performance comparison of models on ImageNet and ImageNet-D. The key features of ImageNet-D that make it unique and the challenges of the dataset. Evaluation of the dataset based on the FAIR principles. Let's dive in. Let me take you back to 2009, when the field of computer vision started to develop dramatically. A dataset called ImageNet was introduced, containing millions of labeled images across thousands of categories. It became the foundation for training and benchmarking deep learning models, enabling breakthroughs that powered technologies like self-driving cars, facial recognition, and many others. ImageNet was used to train and test machine learning models in various computer vision tasks like image classification, object localization, and object detection. They could even exceed human-level performance on some tasks. But as these models became more powerful, a critical question emerged. Could these models handle the complexity and unpredictability of the real world? To answer this, researchers extended ImageNet into variants like ImageNet-C, which added corruptions like noise and blur, and stylized ImageNet, which challenged texture biases by altering image styles. Each of these benchmarks was a step forward, revealing gaps in robustness. But they had their limitations. ImageNet-C, for example, focused on specific and predictable variations. Stylized ImageNet addressed texture bias but couldn't control other factors like background or material. This is where ImageNet-D comes in. By leveraging the power of diffusion models, ImageNet-D introduces an entirely new way to challenge neural networks. It generates synthetic images with diverse combinations of background, texture, and material, creating test cases that mimic real-world unpredictability. Let's break down how ImageNet-D was created. Now, let's have a look on ImageNet-D creation framework, which involves image generation by diffusion models, hard image mining, quality control, and challenge new models. But before that, let's know more about diffusion models. Diffusion models, like Stable Diffusion, generate high-quality images based on textual prompts. These prompts define objects and nuisances like background, material, or texture. They work by simulating a two-step process. Noise addition. Images are progressively corrupted with random noise over many steps until they become pure noise. Denoising. A neural network, trained to reverse this process, removes the noise step by step to reconstruct the image. Let's come back to the creation framework of ImageNet-D. Imagine you're tasked with creating an image for a category, a chair for example. But instead of placing it in a typical setting, you want to test how robust a neural network is when that chair appears somewhere unexpected, like a forest. The process begins with a diffusion model. Using a text prompt, a chair in a forest, the model generates several high-quality images of chairs. Each chair is placed within a forest background, and subtle variations are introduced. The lighting changes, the chair's material shifts, or the forest itself varies in density. These variations create an initial pool of candidate images. Next step is hard image mining, where the images are tested on a set of pre-selected neural networks. Let's say an image of a black metal chair under low sunlight causes multiple networks to fail. They incorrectly label it as a bench. Such an image is identified as a hard image, one that consistently challenges these models. Only these difficult examples move to the next stage. To ensure the dataset is meaningful and accurate, human reviewers step in. For each image, they verify two things. Is the main object, the chair, clearly recognizable? Does the image align with the prompt, a chair in a forest? If an image passes these checks, it's included in the final dataset. If not, it's discarded or refined. Finally, the curated dataset is used to test new models. These hard images, like a black metal chair in a forest, consistently expose weaknesses, revealing how well or poorly the models generalize to complex, unfamiliar scenarios. From diffusion-generated images to rigorous quality control, the creation of ImageNet-D ensures every image contributes to a meaningful evaluation of neural network robustness. Let's take a closer look at how ImageNet-D challenges even the most advanced models. When tested on ImageNet-D, models experience significant accuracy drops. VGG19, a classic convolutional model, sees a staggering drop of around 52%, going from almost 63% on ImageNet to just above 10% on ImageNet-D. ResNet 101, another popular architecture, drops by about 55%, with accuracy falling from nearly 68% to around 13%. For vision transformers, ViTB/16 drops even further, losing around 60% of the accuracy. Even state-of-the-art foundation models like CLIP aren't immune. The CLIP ViTB/32 model, known for its robustness, experiences a drop of around 42%. The challenge extends to vision language models as well. Mini-GPT-4 and LLaVA 1.5, two of the most advanced multimodal models, each experiences a drop of around 17%. These numbers aren't just statistics. They highlight ImageNet-D's effectiveness in exposing weaknesses across a wide range of architectures, from traditional CNNs to transformers and foundation models. What makes ImageNet-D truly remarkable? First, it generates highly realistic test cases that mimic the richness and complexity of the real world. Following the same example, a chair in a forest. The dataset doesn't just create one version of this, it explores endless variations. The chair might be wooden or metallic, brightly lit or shadowed, surrounded by thick foliage or placed on a forest path. These nuances challenge models to think beyond simplistic object detection and adapt to subtle variations in background, texture, and material. Second, the pipeline itself is general and scalable. Want to add a new object category, like a bicycle? Or test models on new nuisances, like shadows or orientation? With ImageNet-D, it might be as simple as adjusting the input prompts to the diffusion model. The pipeline generates these combinations effortlessly, ensuring high-quality results every time. While ImageNet-D offers a powerful tool for testing models' robustness, it comes with its own set of challenges. The reliance on synthetic data means ensuring alignment with real-world scenarios can be difficult. While the generated images are diverse and realistic, they may still lack some subtle nuances of natural environments, potentially affecting how well the results translate to practical applications. Another challenge lies in the generative models themselves. These models can unintentionally introduce biases, such as overrepresenting specific textures, materials, or backgrounds, which might skew the dataset and the evaluation results. Let's evaluate the dataset based on the FAIR principles. The FAIR principles, findability, accessibility, interoperability, and reusability, are guidelines designed to ensure datasets are easy to locate, share, and adapt. Let's evaluate ImageNet-D through the lens of these principles. First, ImageNet-D is findable as it is hosted openly on GitHub and Hugging Face, allowing everyone from around the world to find the dataset and download it. Second, the dataset is accessible, since it has the MIT license which enables anyone to download and deal with it without any restrictions. Next, ImageNet-D is interoperable. It is compatible with a wide range of architectures, from traditional convolutional neural networks to state-of-the-art vision transformers and multimodal models. Finally, it is reusable. The dataset's flexible pipeline allows researchers to effortlessly add new object categories, backgrounds, textures, or materials. In summary, ImageNet-D is a significant advancement in benchmarking neural network robustness. By leveraging diffusion models, it creates diverse, high-quality test cases that challenge even state-of-the-art models across various architectures, from convolutional networks to vision transformers and multimodal models. ImageNet-D introduces a more controlled and scalable way to evaluate model generalization by altering background, texture, and material properties. As AI continues to evolve, datasets like ImageNet-D play a crucial role in pushing the boundaries of what neural networks can achieve. They help uncover hidden vulnerabilities, improve model reliability, and develop architectures that can better adapt to real-world complexities. If you're interested in exploring ImageNet-D further, be sure to check out its GitHub repository, where you'll find more details about the dataset and how to use it in your own research. We hope this video has provided you with valuable insights into ImageNet-D. Thanks for watching.